Hello, everyone. Today, Alina, Kyle, and Manish are presenting the paper named "How Can I Explain This to You?" An empirical study of deep neural network explanation methods. This paper was written by the following authors and was published in New IPS 2020 conference. The corresponding code is provided here on GitHub. First, we're going to introduce this paper by going over study details and key contributions. Then we will go over the unifying visual explanation methods across input domains, such as the model agnostic methods, model transparent methods, and training data-based explanation methods. Then we will go over study methodology, study results and discussion, conclusion, and for and against points. So interpreting or explaining deep neural networks remain a challenging problem due to their high complexity. Its structure often provides little to no insight on the actual underlying mechanics. Models that generate high-stakes predictions, sensitive decisions, often mandate a sufficient accompanying explanation. For instance, robot radiologists now provide superior MRI and X-ray image classification. A life or death diagnosis undeniably justifies the use of the best performing model. However, it is unreasonable for either a patient or medical professional to simply accept an automated prediction. With the inclusion of privacy regulations, including the GDPR, right to explanation, such an explanation is not only desirable, but also legally mandated. In this paper, the authors further investigate which style of explanation is preferred by end users. In this paper, the authors performed a cross-analysis Amazon Mechanical Turk study to compare 6 popular state-of-the-art explanation methods across 4 distinct application domains to determine which styles are most preferred in understanding DNN model decisions. We define an explanation as an image, text, or other visual aid that accompanies a prediction to offer intuition for the model's output. Previous works have introduced several alternative approaches to provide such insight into a DNN model inference. The authors chose 5 previously introduced explanation methods, such as Line, GradCam++, Anchor, SHAP, Saliency maps, and they developed explanation by example method, as there were no explanation by example implementation really available. Their studies span 4 different application domains, such as image, audio, text, and sensory analysis data. In this paper, the authors provided a unification, comparison, and analysis of existing explainability approaches for DNNs across various application and input domains. They also presented and discussed the results of Mechanical Turk study, identifying the relative preference of explanation styles by an average non-technical end user. They offered an open source library called Ex Machina, providing a readily available and widely applicable implementation of explanation by example. Each study question compared 2 explanation methods for a test input, and the participant was instructed to select the method that they considered to offer a best explanation. The authors used the following filtration technique. If the questionnaire was completed too quickly, or if 20% of the validation questions were incorrect, then we simply filter out such responses. And also this part will be covered more in details later. Every method was fine-tuned with optimized hyperparameters such that each method performs in the best possible way. Finally, the authors implemented explanation by example method and offered an open source library called Ex Machina. Well, traditionally, DNN explanation frameworks emphasize their application over input domains that are naturally visualizable and understandable, for example, images or text. But DNN can also be applied to time series data, for example, sensory data that humans may struggle to reason about. The authors seek a unified representation such that an arbitrary input domain's explanation can be visualized and presented to end user. Just like I mentioned before, they chose 4 different domains: image, text, audio, and sensory data that provide insight subset of the popular DNN use cases and enable some better understanding of the benefits of a particular approach. Now, let me quickly go over the GradCam++ method. So in order to generate a visual explanation for the corresponding class label, we use a weighted combination of the positive partial derivatives of the last convolutional layer feature maps with respect to a specific class score as weights. This method gives insight into what the network focused on, and it works with any deep CNN, where the final function YC is a differentiable function of the activation maps AK. Now, let's take a look at this picture. So here we have the original image, and here we have image with the GradCam applied, and here we have the image with the GradCam++ applied. So simply GradCam++ is the better version of GradCam, and as we can see that GradCam++ considers the larger region to be the most important one. Now let's quickly go over Saliency maps. Saliency maps are usually rendered as heat map, where hotness corresponds to regions that have a big impact on the model's final decision. The original Saliency map algorithm is called vanilla gradient that consists of 3 steps. So forward pass with data, backward pass to input layer to get the gradient, and rendering the gradient as a normalized heat map. So let's take a look at the picture. Here we have the original image, and then we have the image of Saliency map blended with original image. And finally, we have the Saliency map itself. Now I'm going to give the control to Manish, and he will proceed with the presentation.
Thank you, Alina. So let's take a look over the remaining methodologies that the authors have explained in this paper, that the authors have used to compare their methodology within this paper. So let's take a look at LIME. So LIME is—
Can you talk louder? A little bit, louder. Yeah. Come close to the microphone.
Yes.
Yes.
Is it better now?
Yeah.
Okay, thank you. So LIME is locally interpretable model agnostic explainer. So in this, what we do is we perturb the input of the data samples and observe how the prediction changes. So one sec, let me use the laser pointer. All right, so let's take a look at the original image on the left. What we do in this case is we divide this original image into different parts of contiguous pixels, and once we do that, then in this case we turn off some of these parts and then feed this image again to the model and see its output, and the model is correctly able to identify it as tree frog again. So all these parts are given the weight, high input weight, and then in the next iteration we turn off some other parts and turn on the other parts, and we see that the model is not able to correctly classify now. So these parts are assigned lower weights, right? And overall we keep on doing this until we finally able to generate an explanation of which is the most important features the model looked into for generating the output. So this is how LIME works. However, there are two simple drawbacks of LIME. The first one is it is only applicable to linear models, and the second one is the type of modification that needs to be performed on the data to get proper explanation are typically use case specific. Let's take a look at anchors. So the thing about anchors is that they were proposed in the same paper in which LIME was proposed, and it was proposed by the same authors. So let's see how anchors are different from LIMEs. So let's take a look at this input dataset. So this is the dataset of Titanic, and the model is trying to predict if the particular person survived or not. So the model was inputted with all these features, right? And what anchors does is, so anchors explain the prediction by finding a decision rule that anchors the prediction or supports the prediction, right? So the output that we get from anchors is this. So anchor explains that if the sex is female and the class is first, then the model is going to be predicting survivor is equals to true. So resulting explanations are expressed as easy to understand if-then rules. These if-then rules are called anchors, right? And how it is different from LIME is a rule anchors a prediction if changes in other feature values do not affect the prediction. So what it means is if you change the ticket price over here, then it should not affect the output over here. So anchors also uses reinforcement learning techniques and graph search algorithms to recover from the local optimum. Okay, let's take a look at SHAP. So SHAP is Shapley Additive Explanations. Again, let's take a look at the example. So here we have on the left hand side is the output, and how SHAP explains the model's prediction is by giving answer in two different colors and different intensities of these two colors. For example, take a look at this 0. The most important point to note in the 0 is that this space in the circle is important for the model to predict it as 0. So the red pixels increase the model's output while blue pixels decrease the output. That means if there's a blue in the image, that is contributing negatively to the output, right? While red contributes positively to the output. And you can see here in the 4, the 4, to predict the 4, the space between these two edges is really important for it to predict 4. Okay, now let's try to compare all these methodologies that we just discussed and try to see how what authors used their method of explanation is different from all these methodologies. So let's take a look at the input image. So this input image is ship, but so how GradCam explains that why model predicted as ship is like this. So it gives us a heat map, and the dark red and black dense regions explain these were the most important features for it to predict a ship. Saliency maps use the same methodology pixel wise. Line explains it in different parts of the image that were most specifically contributing to the ship. The same goes with anchor, and in case of SHAP, they use these dark red regions of the image explaining the most highest intensity values that contributed to the ship. However, all these methods work on a very common outcome, on a very common output, that is superimposition. However, explanation by example is a whole another way of explaining the output. So how explanation by example works is that, so it tells that in my input dataset, I have learned that these particular images belongs to ship, and the image that you input most closely resembles to these 3 particular images in my dataset. And because the image that you input most closely resembles to these 3 images of ship, that's why I'm going to call this as ship as well. So the explanation was given based on the input that you gave to the model. Let's take a look at text input. Again, cooking with my stepfather, is it a positive or a negative sentence? So line tells that cooking with are very positive words, while stepfather and my are positive but lesser positive. So overall, they tell that the sentence is positive. The same goes with anchor and in case of SHAP. However, explanation by example says that I have learned these sentences to be positive, and because these sentences are positive, then I would say cooking with my stepfather is also positive. And these sentences are from its input dataset. Again, let's take a look at the sensory input data. Almost the same thing. So GradCam tells us that these are the input parts of the input image that the model looked at to tell that this is a normal heartbeat. Same with Saliency maps and SHAP. However, explanation by example says it's a normal heartbeat because in input data it has these, And these images most closely resemble to our input image, and these were labeled as normal heartbeat. So this will also be labeled as normal heartbeat. So this is how explanation by example works. Let's take a look at a unified representation of visual explanation frameworks. So what we usually have for explanation is a pre-trained DNN model, F, and it maps input data X for domain D to a set of labels Y, right? And then explanation can be termed as model's metadata, how the metadata of the model. So metadata can also be called as component of DNN that has been utilized for the prediction, right? So if the input is not in the visual domain, then even then the explanation needs to be mapped to the visual domain. Otherwise, the end user will not be able to interpret it and tell how the model was able to predict this. So for this, we usually had the superimposition based explanation methods that we just looked into. So they usually supported image and text data. But what do we do when we come to audio data or sensory data? So the explanation for audio and sensory data was presented in the visual form in the form of time series. So in case of time series, what we do is the signal waveform is presented on a graph and how that signal waveform is changing with respect to time. This methodology is called time series. So once we are able to plot these waveforms on this type of a graph, we can then use these superimposition based explanation methods to explain the outcome of the model. For example, take a plot of an ECG input sample. Let's take a look at it. So this is an input signal waveform that is changing with respect to time, and how AI is able to break down. So there are lots of medical terms in it which we don't need to focus on, but how AI based arrhythmia detector is explaining its decision is like this. So it's able to break down this image into various different parts, and then it can tell which of it is QRS complex, and based on this it can detect whether the person has arrhythmia or not. So let's take a look at what author's method actually is. So author's method is not a superimposition based method, but it's a training data based explanation method. In this case, explanation by example framework focuses on various aspects of the DNN model as well as the training data set. So the general function for explanation does not outcome in the same input image with superimposition, but it outputs a set of examples from the input dataset, and it is applicable to all the different domains, that is text, input, image, audio, and sensory, any type of data. And then the output is based on the nearest matching example in the training data with the highest cosine similarity with the text inputs. Finally, let's compare different methods across different input domains. So these superimposition based methods are divided into two different categories called model agnostic and model transparent. So line, anchor, and shape are model agnostic, while Saliency maps and TradCam are model transparent. So model agnostic treat the model like black box and the approximate relationship between input and output prediction. Our model transparent superimposition methods have access to DNN pipeline, that is, they have access to inside of the model, right? And they focus on the relationship between input and output as well as the associated activation of the hidden layers. Now I'll give the control back to Alina. Thank you.
So from here, we'll discuss the study methodology in a little detail. So we know they focused on 4 input domains. And for each of these domains, they considered one data set. So practically, they conducted 4 separate Amazon Talk studies, one for each domain. The study questions were presented in a way like each participant was presented with a random test input and a model predictor class. So they provided a participant with a random test input, and they also provided with a predictors class. Along with that, they provided any two randomly selected explanations. So for every test input, we can have two explanations from those 6 explanation methods, right? So now the participant has to select out of the 2 presented explanations, he has to select the one that he thinks is better, and that he thinks that that explanation is able to define the decision of the model. So it's more about what the participant is understanding and what the participant thinks is a better explanation. So the number of questions that each participant answered varied across each questionnaire because the time that a participant requires to parse the test input and the explanations varied for each of the participants. That's why each participant answered different number of questions for every questionnaire. So we had for 4 tasks, and for every task we had a separate questionnaire. For the image classification questionnaire, we had 15 comparisons. For the text classification, there were 12 comparisons. For keyword classification, there were 6 comparisons. And for the ECG-based arrhythmia heartbeat classification task, there were 12 comparisons in the questionnaire. The authors also tried to validate the responses because you see, this is a study based on the responses of the participants. So it's a possibility that the participants are providing illegitimate responses. So how do they filter this out? They had 2 criteria for that. The first criteria was simply they decided that this minimum, that there is a minimum time that is required to complete the response. So if a participant took lesser time than that minimum threshold, they discarded the responses for that. They did not include that in the study. The second criteria was that they, for each test input, they also provide validation questions. And in those validation questions, they simply ask the participants if they agreed with the model's prediction or not. So you see, for every task we have models, and those models can, like, although we'll talk about the reference scores in a bit later, but these models may give you a correct output, and at times it may give you a wrong output as well. So the participant had to tell if they think the output was correct or not. So this strategy will help because they don't have the true label. They're telling if they think the model is right or not. This will help in cross-referencing if the participant was willing to, if the participant was either willing to understand or it was able to comprehend the provided test input and the model's result and the explanations associated with that pair. So the participants that failed 20% of these validation questions, their responses were eliminated, and those responses were not included in the study. So based on this, they tried to filter the responses. For the ECG and sensor inputs, because we know an average user doesn't have a really good understanding of the sensory data, the ECG-based data. So in that case, they provided the true label, and they asked the participant if they agree with that or not, like if they think it's the correct. So that is just in the case of ECG sensor inputs, not in the case of other domains. Let's talk about the task and the data sets. So we have here 4 domains, right? Image, text, audio, and sensory data. For each of these domains, we have a task. For the image, we have image recognition. For text, we have sentiment analysis. For audio, we have keyword detection. And for sensory data, we have heartbeat classification. So for the image, we use the Superimposition data set that has 10 different classes. For the sentiment analysis task, they use the sentiment 140 data set. It has only 2 classes because it has tweets and their associated sentiments. So a sentiment can either be positive or negative. To maximize the participants' engagement, what they did was they selected shorter text lengths so that it's easier for the participant to process that. For the keyword detection, they used Google's speech commands, and they extracted the 10 most common keywords. So we have 10 classes here, and they made sure that the utterances were only 1 second long to make things easier for the participants again. And for the ECG, ECG data, they use the MIT BIH arrhythmia data set, and the test inputs that they presented to the participants, they made sure that those were easier to be recognized by an average non-technical person. Let's talk a little about the models and the explanations. So for each of these 4 tasks, they trained 4 different CNN models. For each of these models, they had both batch normalization and dropout layers. These are the FN scores that they presented for the task, and these are really good. Like for the image classification task, they had an FN score of 87.8%. For text sentiment analysis, they had 83.5%. For keyword detection, it's 90.2%. And for the ECG heart rate classification, it's 86.2%. So this is actually the FN scores for the models that they trained. And from these models, the results will be presented to the participants. And based on that, the participant can actually respond for the explanations. They also talked about configuring and optimizing explanation methods. So like Alina mentioned earlier, it's very important to configure and optimize these explanation methods so that they perform in the best possible manner. For a fair comparison, they universally selected the activations after the last convolution layer because previous studies recommend that the last convolution layer provides the best explanations. This is a table that we are going to look at. It has two kinds of explanation styles, like we know, superimposition based and explanation by examples. We'll talk about the 6 explanation methods here, and we'll see which of these explanation methods are adaptable to these domains or not. So we'll talk about the methods that are being marked with a check mark, means that they were explicitly designed for that particular specified domain. The methods that are being marked with a cross mark, it means that it was non-trivial to adapt that explanation method to that specified domain. So they could not do that. And for whenever you see a circle, it means that they successfully managed to adapt that specified explanation method to that specified domain. So let's have a look at it one by one. For Lime and Anchor, they were explicitly, it was like easy to adapt these methods to image and text, both of them, but it was non-trivial to adapt these explanation methods to the audio and sensory data domains. Okay, one thing is Lime and Anchor require fine-grained hyperparameter tuning to generate acceptable explanations on images, right? And one more thing was in case of images only, they had to use an addition segmentation algorithm. So they preferred using the Cousins-Wells segmentation algorithm to segment images into superpixels. So that was one overhead that they had to deal with by working with images in case of these methods. For the SHAP method, it was adaptable to the image and text domains, and they managed to adapt it to the audio and sensory data as well. SHAP has different approximation methods to choose from. For the text domain, they use the deep explainer, and for the image, audio, and ECG, they use gradient explainer. They have not defined these in detail in the paper. For the GradCam++, it was explicitly designed for image, but it was non-trivial to adapt it to the text domain, but they could successfully adapt it to the audio and sensory data. And both GradCam and Saliency maps are intended for image classification only, but this is what they did to treat the ECG and audio domains. They treated the samples, the test samples, as a one-dimensional image with only a single channel, and then they normalized the values between 0 and 1 to extract explanations in case of both ECG and audio data. In the end, they provided their own implementation for explanation by example, the Ex Machina explanation method. It was adaptable to all of the 4 domains. So results, let's talk about the results. We'll see the result of each of these explanation methods for across all 4 domains. So we can see the Lime was adaptable to image and text domains only, and it was performing really good in the text domain. It was preferred by the participants 70.4% of the times when it was an option. On the other hand, the results for the image domain were not really good. For the Anchor, the results for both the domains were not good, and for the audio and sensor, we don't have any results because it was not able to adapt this method to these domains. For the SHAP, they were able to successfully adapt it to all domains, but you see the results were not really good. In case of image, audio, and sensor especially, only the text study had a better, participants preferred it almost 60% of the times, but still it was not as good as Lime. For the Saliency maps, again, the results were below 50%, like participants preferred it lesser times compared to other methods. And for the GradCam also, it was adaptable to image, audio, and sensor, and it was not preferred more than 50% of the times for any of the domains. For the Ex Machina, the results were really good. In the image domain, the participants preferred it 89.6% of the times. In the audio domain, it was preferred 70.9% of the times. And in sensor, it was preferred 84% of the times. While the results were not really good for the text domain, it was preferred like in 3 out of the 4 domains. So if we look at this whole thing and combinedly, we can say for the text study, Lime was performing better than the rest of the 5 explanation methods. And explanation by example, their implementation Ex Machina was performing better in the remaining 3 domains with these preferences of the user. So they have used 95% bootstrap confidence interval to represent this. Let's talk about the usability and stability of explanations. First, we need to understand what an unstable explanation is. If you are giving if you are giving the same input to a particular method, and the method is giving you different explanations for the same input, that means the method is giving you unstable results, right? So Lime and Anchor were both giving unstable results, and the author says that this could be due to the inconsistent. This could be due to the reliance for the image domain specifically. This could be due to the reliance on the segmentation algorithms. And although for the text domain, we don't need to use a segmentation algorithm, because you see the granularity of words provide a natural unit of semantic value. So the author says that one common thing in both the domains was that these methods require highly tunable, like you have to optimize them, right? So they're highly tunable methods, and which is why they have an increased configuration complexity and a higher probability of suboptimal specification. So one thing in case of images, one extra thing is the reliance on segmentation algorithms, but overall they claim that these methods, Lime and Anchor, are unstable because they need to be optimized. They require a lot of effort for optimization also. The other thing is stability, which is just the opposite of unstability. So if you are giving the same test incident to a particular method and the explanation that they are giving you is the same, that means that particular method is stable. In our case, out of those 6 methods, 4 were stable. GradCam++, Saliency, Maps, Shep, and explanation by example were all giving stable results. And one reason is they required no fine-grained hyperparameter tuning. The only configuration parameter that was required was a model layer to use in generating explanations. So this can be concluded that due to less configuration complexity, these methods are significantly easier to use compared to Anchor and Lime. I'll transfer the control to Kyle now.
All right, 1 second. Okay, so for the idealized versus actualized explanations for the superimposed methods, GradCam, Saliency Maps, and the SHAP highlight the input features important to the predicted classification. This can differ from normal human intuition. Similar to the previous bullet, Anchor and Lime mask features that humans may find important. An example in a reading was given a picture of an airplane in the sky. Models may find the sky surrounding the airplane to be most important feature to classify the object as an airplane, where most humans may prefer selecting the airplane as the most important feature. Continuing with this idea, for audio data, these methods emphasize sections of input without speech. And in ECG data, flat sections may be highlighted instead of actual heartbeats. So for the explanation by example, the nearest training example for images were usually very similar to the input image. This was found to be the same for audio and the ECG data. Yeah, they were maxing pretty similar. The main limitation of explanation by example is the quality of the training data. If the training data does not have enough similar examples, then the explanations will be subpar. This can be seen in the text domain where the explanations were unrelated. But despite this, explanation by example is preferred over the alternatives. So like I mentioned, the text domain explanation by example didn't do a very good job. The preferred method was actually Lime, and Lime provided an annotation and word association that closely matched the human intuition. One negative was when Lime assigned sentiment to words that humans consider neutral. This was also the case with Anchor, and this is just showing an example. We've seen this image before. The final thing we're going to talk about is actually privacy risks. So since explanation by example requires access to the data used to train the models, there exists a possibility that the data may be used for unintended purposes. Exposing sensitive training data that can identify a person or information about a person can become a severe privacy risk. It is important that the data exposed does not violate a user's privacy. And there are a few different techniques that can be used to protect training data, but doing this does impact the quality of the explanations. So in conclusion, explanation by examples in Lime are the preferred explanation method. The input domains explained compare features across a test input and similarly mapped ground truth examples. In the text domain, Lime's method was preferred. And although the other studied methods have good performance, they failed to provide a more desirable explanation. So the four, by selecting image, text, audio, and sensory data, they considered a subset of the popular use cases. Explaining neural network models in human intuitive manner is important, and not a lot of research is done in this domain. Results in favor of explanation by example are intuitive. It highlights the importance of hyperparameter optimization for explanation methods, and the code is available on GitHub. The against is considered only a single data set for every domain. Didn't discuss other popular methods like LRP. All 6 explanation methods were applied to images, but some were not applicable to text, audio, and sensory data. And it presented visualization of just one example per domain. More examples, both positive and negative, would have been helpful. And this kind of evaluation is purely from an end user experience perspective, and it can be prone to subjectivities. So that was the end of our presentation.